Okay, in our session 7 lab, you're going to learn to fit a Cox proportional hazard model, um, create a stratified Kaplan-Meier plot, and we'll briefly touch on fitting exponential and Weibull accelerated failure time models and fitting a model using strata and a time-dependent covariate. And then finally, this isn't really related to the rest of this session, but I wanted to show you how to create a directed acyclic graph using dagitty and importing it into R. So first exercise, fit a Cox proportional hazard model to the leukemia 6MP clinical trial data set, like the one we used in the lecture. So I'm going to go ahead and load these packages, survival, survminer, and tidyverse, and then read this data set. All right, so let's take a quick look. I'll do view Luke. It's a very simple data set, just time, censoring, and group. So time, this is the time in weeks. The censoring variable, this is 1 for an event and 0 for censoring. And the group is just 6MP or placebo. That's it. So first, create a stratified Kaplan-Meier plot. So we're going to use the survival package for all of these things. For the Kaplan-Meier plot, I use this survfit function. And the y variable here, I have to use this capital S serve function to create our survival outcome. So just to show you what this means, I'm going to do with Luke serve time sense. It creates this object that has pluses by the censored event. So if I were to look just at Luke, well, we see that the 10th observation is a time of 6, and it's the first one that is censored. So that's this event here. So it's just being represented a little bit differently. Instead of 2 columns here in a tibble, it's just a vector of times with a plus after the censored variables. Don't confuse this with like a character variable like 6 plus. Ordinarily, when you saw that, that would be like a character. This is something, it's just a special object, and it has the same information as these 2 columns. It's just a way of telling R that this is a time to event, and some of these are censored. So with that fit, we can use this ggservplot function from the survminer function to create the Kaplan-Meier plots that you've been seeing in the lecture. Oops, I have to run this first one, and now I can run our Kaplan-Meier plot. Let's see, what is this? So this is kind of a funny thing that I've noticed with some of the functions that work on output from the survival package, that some of them don't work when you use the double colon on the survival analysis stuff. And this came up, I noticed it later, that normally I would have put survival colon here. But in order to use these in the stargazer function, I had to get rid of that. And I think it's the same thing here. So apologies. Anyways, I'll hide my image here just so you can see the output. Here's this nice stratified Kaplan-Meier plot with these 2 groups and the risk table at the bottom. All right. So not much to that. This, by the way, if I look at KM fit, it just has this number of events with a median and the median number of or the median survival and a confidence interval on that median survival time. And the summary, well, this is just a bunch of data. It's actually the Kaplan-Meier estimate at each time for each of the groups. So all that stuff that we had done in a spreadsheet last week, we can get for free here just from this summary KM fit. And we can plot it using this ggserv plot from the servminer package. Okay, next question. Fit exponential and Weibull accelerated failure time models. Maybe I should add Cox pH, exponential, and okay, because I actually do fit, might as well fit the Cox proportional hazards model here too. So just like above, we have this serve times sense as the y. The rest of this is just like LM and GLM as you've been using. And then for the parametric models, all we have to do is use this servreg function, also from the survival package, and specify a distribution. So that's all there is to it. When I look at the summaries of these from the Cox proportional hazards model, you remember we have this very negative coefficient, a hazard ratio of 0.2, or an inverse hazard ratio of 5, saying that the hazard for the treatment group is much lower than it is for the placebo. Looking at one of these other plots, the exponential parametric plot. So before let's see, we had a hazard ratio of 0.2. In this one we have let's see, we have oh, sorry, I just do this again. Okay, let's look at that again. So for Cox pH, we had a coefficient of negative 1.57. For the exponential model, we have a coefficient of plus 1.527. So it's pretty close. And you notice again that they differ by a sign because this is a survival ratio, so telling us that the interpretation of this would be that patients in the treatment group, 1.527, live 4.6 times longer on average than patients in the placebo group. So it has a nice interpretation to it, and we see in this case that that it's pretty close to the hazard ratio with that difference in sign. In the Weibull fit, we have this additional log scale. That's an additional parameter being fit to the baseline hazard. And we see a somewhat smaller but still quite significant survival ratio, or log survival ratio, for the treatment group. This I'll save. This looks good in the built version. It doesn't look so good here. Just to say, so when I run it here, you get a bunch of HTML. But if I put this results equals as is in the chunk, then in the built version, like if I do knit, this comes out as a nice HTML table. And I'll just mention here that it is possible to assess the fit of how well the parametric model fits your baseline hazard by comparing it the the survival curves that you get from the parametric model to your Kaplan-Meier estimates. I don't actually do that here, but it can be done. Oh, just to show you, let's see, our nice stargazer table where you can see you can compare these coefficients between the models. And I would say, given how similar these are, I would feel quite comfortable using the exponential failure time or the exponential hazard function here. It looks like I'm getting very similar results to the Cox proportional hazards model. Okay. Note, I wouldn't compare the likelihoods between the Cox and the AFT models just because they're completely different kinds of models, and I'm not sure about comparing likelihoods between those. I'm comfortable comparing likelihoods between nested Cox models or between nested AFT models, like with different coefficients but the same kind of model, but I wouldn't actually compare across these types of models. Okay, fit a stratified Cox proportional hazards model with a time-dependent covariate using an example from Cox PH. Just to make this easy, I decided to use an example from Cox PH. They have a few examples. This is just the first one. So I copied their code here to create a test data set. So we've got some times here. They're either 1, 2, 3, or 4. Status is the censoring variable, so 0 is censoring, 1 is event. X here is the time-dependent covariate, and sex is a non-time-dependent covariate. So X is just something that for any individual can vary as a function of time. So fitting a Cox proportional hazard model to this is easy. We just use X as our predictor, and then I'm also stratifying by sex. So what does that do? It's going to fit a different baseline hazard function for sex equals 0 and sex equals 1, whatever that means. But it's as easy as that, just having in your model formula plus strata sex. And when I fit this, maybe I'll do a fit, and then I'll do summary fit. You see that I still get a unified estimate for X here. So the effect of X has essentially been estimated in each of these strata and then averaged across the strata. Okay. Now, I'm not really getting into DAGs in this course because you get plenty of that in your EPI courses, but I just wanted to show you a bit about drawing a DAG, especially because this software is so great. It has a great web page, dagitty.net, that produces code that you can then put into R and produce in your R Markdown document. So I'm just going to show you a little bit the web page, dagitty.net. I'm going to launch Dagitty, and they've got an example here. So in their legend here, this green right angle, that's an exposure. The blue with the vertical line is an outcome. This is an ancestor of the outcome, an ancestor of the exposure, and then z is some other variable. But the nice thing about this is that if I enter my causal dag here, it will just tell me what I have to do to adjust for total effect, direct effect, or an instrumental variable analysis. So in this case, because we have a direct effect of the exposure on the outcome, and we have no confounders. That is, there's no variable that causes both the effect and the outcome. No adjustment is necessary to estimate the total effect of E on D. If I were, however, I'll just show you. If I were to, well, I'll maybe add a line here. Now, as a minimal adjustment, A is now a confounder, so it tells me I would have to adjust for A. And it also tells me testable implications. That is, these are null hypotheses that I could test. So one of the hypotheses that I could test based on the assumption that all of these are measured except for Z. For example, I can test for independence between A and B, between B and E, etc. These are testable hypotheses. I don't even know what this R code is here. Testable implications. Wow, it just makes a table of this for you in R. But let me show you, if I were to make something between Z and D. Now I have two confounders, A and Z. So I would have to adjust for both of these in order to estimate the total effect of E on D. So pretty cool. Now, if I make Z unobserved, then the total effect cannot be estimated by covariate adjustment. So very practical. Does a lot of stuff. I don't know what all of this stuff is. It's very powerful. But this model code here, this is stuff that you can paste and put it into R, which is what I've done here. Maybe I'll go ahead and I'll create a new model. I'll make this model that I did here. I did an exposure, and I go click, turn this into exposure. I make disease. Okay, I turn that into the outcome. I hypothesize that, and then I put here a confounder. Okay, and that's going, I'm going to put arrows to both of these, and then I'm going to make here a collider. And that's going to be something like this. Now I can see that the adjustment for total effect, all I need to adjust for here is the confounder. If I were to put something here like mediator, okay, and I'll put there. Same thing. Now, if I want the direct effect, I'm going to have to adjust for both the confounder and the mediator. But for total effect, that is the total effect of exposure on disease, I still only need to adjust for confounder. So super helpful. It both tells you something about what you should adjust for in your model, and it gives you this code that I can take I can put into my model. All right, and now I'm going to plot, and there it is, that thing that I just made. It's not quite as fancy as it was on the web page, but here it is. I've created a DAG in R. Pretty nice, right? All right, that's all for now. Thank you.